Welcome to AI Paper Slop. Today we are jumping straight into a fascinating paper from Stanford University. It's called AutoMem, Automated Learning of Memory as a Cognitive Skill.
Yeah, this is a big one.
It really is. And, if you're an AI researcher or an ML engineer listening to this, the core insight here is basically a massive paradigm shift.
Yeah.
Instead of treating an LLM's memory as this, fixed architectural module, like standard RAG or a sliding context window, AutoMem actually treats memory as an active trainable skill.
Right, which is completely different from how we usually build these systems.
Exactly. So they give the model first-class file system operations, things like read, write, search, and then they use two automated optimization loops to improve both the structure of the agent's memory and its actual parametric proficiency.
And the results are wild.
They really are. Just to give you the bottom line right up front, they took a 32 billion parameter open weight model, Quen 2.532b instruct, and they increased its performance on complex long horizon games by 2 to 4 times.
Yeah, it literally beat its 72 billion parameter counterpart.
Beating a model more than twice its size. And it even rivals frontier models like Claude Opus 4.5 and Gemini 3.1 Pro Thinking.
Which is incredible because, we are really hitting the physical limits of context window scaling right now.
Oh, absolutely.
Brute forcing, like 1 million tokens into a prompt, isn't just expensive for compute. It actually degrades the model's reasoning. The attention heads just get completely overwhelmed by all the noise.
Right. It just loses the plot.
Exactly. So what this paper provides for you guys building agents is a concrete framework. It's a way to build AI that actually knows how to manage its own memory files over 100,000 step horizons.
Which is huge. So I want to dig into how they actually did this, because the whole thing hinges on this cognitive science concept, right?
Metamemory.
But before we get to the optimization loops, we should probably set the baseline. Because normally, if you want to give an LLM memory, you do one of two things.
Right. You either use a sliding window,
where the oldest messages just get pushed out to make room for new ones. Or you build a RAG pipeline, where an external database just, searches for keywords and forcibly injects that text back into the prompt.
Exactly. And in both of those, the LLM is totally passive. It's just having information handed to it.
Right.
But metamemory is the opposite. In human psychology, metamemory is it's the learned skill of understanding your own memory. It's knowing what information is actually worth encoding, when you need to retrieve it, and how to organize it.
So it's active.
Highly active. Like if you're in a 3-hour meeting, you don't just passively listen and hope you remember everything, right? You take structured notes. You review them before you speak.
You're managing your own cognitive load. So how on earth do you translate a human psychological trait into code for an AI?
Well, they put file system operations directly into the exact same action space as the agent's physical actions.
Wait, really?
Yeah. So read, write, search, create, those are in the same vocabulary as move left or attack.
Okay, let me make sure I'm visualizing this correctly at the inference level. Normally, a model outputs a word like attack, and a Python wrapper makes the game character swing a sword.
Right.
You're saying the model can instead output like a JSON command saying create file.map.txt, and the Python wrapper actually interfaces with the local directory to make that file.
That is exactly what happens. The agent essentially runs 2 distinct routines every step. First is the log routine. So it looks at the environment and it has to make a conscious choice. Is this worth recording?
Okay.
Yeah, so it might see a goblin and decide to create a new file, or just append a coordinate to an existing map, and then it runs the plan routine, where it actively searches its own directory to recall info before acting in the world.
So, if I can make an analogy for the listeners here, instead of just giving the LLM a bigger desk, which is basically what a massive context window is.
Yeah, that's a good way to put it.
This is like giving the LLM a filing cabinet and teaching it how to actually use the folders.
Exactly. A massive desk just means you spend 90% of your time scanning the surface for one document. That's what happens to an LLM's attention mechanism. A filing cabinet requires actual attention.
Okay, but as an engineer, this is where I start seeing some red flags.
Oh, sure.
Because if the model has to juggle file management and gameplay in the exact same action space, doesn't that just completely bloat the inference process? I'd imagine the agent just hallucinating file paths or getting stuck editing text files forever.
Oh, it does. If you just give an untrained model a file system, it behaves like a terrible intern.
Right.
It saves everything in the wrong format, overwrites data, hallucinates folders. But that unified action space is actually the secret to fixing it, because every single memory decision leaves a paper trail.
Oh. Because they're explicit text outputs. They aren't hidden inside the neural network's internal state.
Exactly. Every read, write, and search is a traceable action in the log. If it writes garbage, you can see it. And that observable trail is what makes it trainable. Which brings us to the first optimization loop, the scaffold optimizer.
Outer loop 1. Okay, let's break this down. We have this agent with a filing cabinet, and it's currently just throwing loose papers everywhere. Yeah. How does this loop fix the structure?
Well, we have to talk about why standard reinforcement learning completely fails here. It's the delayed consequence problem.
Right, the causality gap.
Yeah. Imagine the agent is in a maze. At step 50, it makes a memory mistake-like. It sees a locked door but forgets to write down the coordinates. Or it formats the notes so poorly it gets buried.
And that mistake at step 50 might not ruin the run until, like, step 800 when it finally finds the key and has no idea where the door is.
Exactly. And standard RL just gives a scalar reward, like Megiddo 1 when you die at step 800.
Yeah.
The model has no idea that the fatal error was a sloppy text entry 750 steps ago.
So how do you bridge that gap?
They bypass scalar rewards entirely. They bring in a strong meta LLM, in this case, Claude Opus 4.6.
Oh, wow. So Claude is acting as, like, a code reviewer.
Essentially, yes. A senior code reviewer. It doesn't look at simple scores. It reviews complete episode traces. We're talking up to 100,000 steps of action logs, the resulting memory directories, and the actual Python code of the agent's scaffold.
That is an insane amount of data for Claude to parse. What is it even looking for?
It diagnoses failure patterns. It traces where the agent got stuck, works backwards through the log, and figures out how the file system failed. And then it iteratively rewrites the agent's Python code and the memory file schema.
It physically restructures the filing cabinet.
Yes, and it tests these revisions on fixed seeds. It only keeps the new code if the AG's progression actually improves.
You know, the NetHack example in the paper really made this click for me. For anyone listening who doesn't know, NetHack is this insanely complex, procedurally generated game from the 80s.
It's notoriously hard for AI.
Super hard. And the base agent in the study was basically using an append-only text file to map the game. Every time it took a step, it just appended a new sentence describing the room to the bottom of the document.
Which is an absolute disaster for context limits.
Right. If the agent paces in a hallway for 20 steps, it writes 20 separate sentences describing the exact same walls.
The context just overflows with redundant tile coordinates. The useful stuff gets buried, and the agent dies almost instantly, usually at experience level 1.
Yeah, but then Claude Opus 4.6 analyzes that trace, sees the massive bloat, and rewrites the Python logic to use a coordinate-keyed map deduplication format.
Right, let's clarify that for the listeners. Instead of chronological sentences, Claude rewrites the code to maintain a clean 2D dictionary.
Exactly.
So if it sees a door at X.4, Y.2, it updates that specific key. If it looks at the door again a minute later, it just overwrites that exact same key.
It's maintaining a live grid instead of scribbling in a diary.
Yeah.
And just from that one structural change, the agent survived for 7,000 steps and reached level 2.
It's incredible context compression, but this actually reveals the next bottleneck.
Okay, what's that?
Well, Outer Loop 1 gives us a perfectly structured filing cabinet. The folders are perfectly labeled, but a perfect cabinet is totally useless if the clerk using it still doesn't know how to do their job.
Right. I mean, the model itself still has to decide when to search for the door or what items are important enough to write down. The schema is just the container.
Exactly. Which brings us to Outer Loop 2. If the first loop fixed the code, this second loop targets the model's parametric weights. We are actually training the neural network's proficiency now.
Okay, but how do they get the training data for that? You can't just have a human manually annotate 100,000 steps of file system logs.
No, you'd go crazy. The meta LLM steps in again. But this time it acts as a training engine. It reviews a massive pool of traces from the agent's own exploration, and it curates only the high-quality memory decisions.
The moments where the agent actually used the files correctly and progressed.
Yes, and then it orchestrates a supervised LoRa fine-tuning to force the model to absorb that curated data.
Real quick, just to define LoRa for anyone newer to this, it stands for low-rank adaptation. So instead of updating all 32 billion parameters, which is wildly expensive, You freeze the main model and just train a tiny adapter module that plugs into the network.
Right, it's highly efficient. And that efficiency enables the most fascinating architectural choice in the whole paper.
The deployment split.
Yes. During inference, they run 2 instances of the model sharing one conversation history. You have the trainable LoRa adapter acting as the memory specialist. It handles all the file system reads and writes. And then you have the frozen, unmodified base model handling the actual physical gameplay.
Okay, wait, hold on. If I'm an ML engineer listening to this, I'm screaming right now.
Yeah.
Maintaining a dual model handoff during inference sounds incredibly complex.
Oh, it's a routing nightmare, yeah.
Why not just mix the curated memory data with the game action data and fine-tune one single unified agent?
It's a totally valid pushback, but the split solves 2 massive problems. First, if you mix the data, the gradient signal gets diluted. The optimizer is trying to teach the model how to format JSON and how to swing a sword at the same time.
Oh, so splitting it keeps the LoRa training purely focused on memory.
Right. But the second, much more important reason is protecting the base model.
From catastrophic forgetting.
Exactly. Qwen 2.532b is pre-trained on terabytes of internet data. It already knows physics, logic, coding. If you run a massive fine-tuning job to teach it NetHack file structures, you risk overrating its generalized intelligence.
It becomes an amazing memory clerk, but suddenly forgets how to walk through a door.
Exactly. By keeping the task model completely frozen, you guarantee it retains 100% of its world action abilities. The memory capability from the LoRa adapter just stacks cleanly on top.
Okay, that makes a lot of sense. You get the perfect cabinet from loop 1, the perfect clerk from loop 2, and you don't lobotomize the worker who actually plays the game.
That's the complete AutoMem architecture right there.
So we have the theory. What actually happened when they ran this? And we should note, they tested this on procedurally generated games. The maps change every time, so the model can't just rely on its pre-training data. It has to actually perceive and remember.
And the empirical payoff is massive. In Crafter, which is like a 2D Minecraft survival game, the base agent's progression went from 25% to 51.4%.
So it basically doubled its capability.
Yeah. In NetHack, it jumped from 7.5% to 30%. And in NetHack, it went from 0.42 to 1.85%. And remember, this heavily optimized 32 billion parameter model is beating the 72 billion parameter version of itself.
And rivaling proprietary frontier models. But, the pure progression numbers are great, but the behavioral metrics are what I found really fascinating.
Oh, the telemetry is amazing.
Because it shows why it improved. The rate of what they call unproductive actions, like oscillating in a room or getting stuck in a corner, dropped by 32 to 65%.
Because it actually knows where it is. It stopped wasting time re-exploring the same empty areas because it finally had a reliable map.
And the efficiency gains on the file system side are just as crazy. The rate of repeat redundant memory writes dropped by like 68 to 83%.
The LoRa specialist stopped writing down the same useless facts. And the empty search rate, where it queries for an item that isn't there, which wastes a whole inference step, that dropped by up to 50%.
Which ties into probably the most counterintuitive stat in the whole paper, the context compression.
Right. You'd think forcing an agent to constantly read and write text files would just bloat the context window with JSON syntax.
Yeah, that was my exact thought earlier. But because the schema was deduplicated by loop 1 and the behavior was optimized by loop 2, it actually compressed the input context token count by 25 to 30% per step.
A smarter memory system literally compresses information. The base model only sees the exact snippets it queries for. It's not diluted by thousands of tokens of raw observation history.
To bring all of this together, I want to share the specific Crafter example from the paper because it beautifully shows how these loops compound.
It's a great example.
Right, so if you run the base agent, it just loops on survival, wanders around, gathers some wood, maybe builds a pickaxe, and then dies to a zombie or starves. It gets like 2 out of 22 achievements.
Because it operates purely on immediate stimulus, no long-term plan.
But then you add just outer loop 1, the Claude reviewed scaffold. Now it has a filing cabinet and the dictionary logic. Suddenly, it organizes its inventory well enough to craft stone tools, build a furnace, and mine iron. It jumps to 12 out of 22 achievements.
And this is the key, if you look at the logs, it hits a ceiling. It gets so obsessed with mining iron that it forgets to eat, and it starves to death in the mines.
The structure is there, but the proficiency isn't. So finally, you deploy the full AutoMem system with outer loop 2. The trained LoRa specialist is running the files. Now, it reaches that same high-level crafting tier, but it actively manages its food supplies to sustain itself.
It hits nearly a 60% progression rate. It learns to balance multi-step resource gathering with immediate survival needs.
Because its memory retrieval tells it exactly when it's hungry. It's amazing.
And when you abstract this away from gaming, the implications for enterprise AI are just massive. It proves that treating memory as a trainable software skill is way more compute efficient than just throwing millions of tokens at a sliding window.
We are teaching the model how to remember, not just buying it a bigger hard drive.
Exactly.
Now, of course, we have to mention the limitations. The Stanford authors are very clear about this. Currently, this relies entirely on episodic memory.
Right, meaning the entire file system is wiped clean at the beginning of every new run. It doesn't carry knowledge across different episodes.
And it's only tested in game environments, which have very strict rules compared to, say, a noisy enterprise code base. Plus, right now, Claude has to optimize a completely separate scaffold for every specific game. There's no universal scaffold yet.
True, but those limitations basically point exactly to where this technology is going next.
And that is exactly what I want to leave the listeners with. Just a thought to mull over. If an AI's memory can be automated to this degree for a single, isolated 100,000-step episode, what happens when we remove the wipe?
Oh, man.
Imagine applying AutoMem to a persistent cross-session memory for a real-world coding assistant. We aren't just talking about a smart filing cabinet for an afternoon. We're talking about an AI iteratively refining a multi-year file system of a company's code base, or your own life.
Learning how to index your thought processes over decades.
The sliding context window is gone. The filing cabinet is permanent. That is all we have for you today on AI Paper Slop. Thanks for listening, and we'll see you next time.